Now another application of Gauss law is to find the electric field due to a uniformly charged infinite plane sheet. So here we consider a uniformly charged infinite plane sheet. So this plane sheet, it has a charge which is uniformly distributed on its surface, and this side extends till infinity, this side also extends till infinity, this side also extends till infinity, and this side also extends till infinity. So if you want to find the electric field due to a uniformly charged infinite plane sheet, say at this point P, which is at a distance r from this plane sheet, then we can use Gauss law to do that. And according to Gauss law, the electric flux through any closed surface, which is given as closed surface integral E dot ds. This is the electric flux through any closed surface, and is equal to Q by epsilon naught. And Q is the charge enclosed by the closed surface. So if you want to find the electric field at this point, then we'll have to enclose some amount of charge in this plane sheet. And to do that, we'll have to draw a Gaussian surface, which in this case we can take a cylindrical body or a cylindrical surface to be the Gaussian surface. So here what we do is we draw a cylindrical body, and this is the end surface. So I'll drop that one off. So this is the end surface A, and we extend this one this side, and this is the other end surface A. So both these surfaces, they enclose some amount of charge Q on this area here. Okay, so these two surfaces, they enclose the amount of charge on this area here, A. Now to find the electric flux using this formula, okay, so first what we'll have to do is we'll have to split this one. You can see here the surface S, which is this cylinder, has three parts. One is this one, S1, the other one is this, S2, and another surface is this one, S3. So here what we'll have to do is this integral, we can write it as closed surface integral as E dot ds. This is equal to surface integral of the first surface E dot ds plus closed surface integral of the surface S2 E dot ds, then plus again the surface integral S3 E dot ds. Now we'll have to find the direction of E dot ds for the surface S1. So at this on the surface, the direction of the electric field E will always be away from the positive charge. So say at this point on the surface, the direction will be away from the positive charge. And ds, the direction, will always be normal to the surface S1. So this will be the direction of your ds vector. And you can see they are in the same direction. Now for this E, for the surface S2, we can take any point here, and again here the electric field will be in which direction? Away from the positive charge. So this will be the direction of your electric field on this point. So I'll drop that one off. So this will be your E vector at this point. Now your ds vector will always be normal to the surface. So ds vector will be normal to the curved surface. So this will be your ds vector. So that is for the surface S2. Then for the surface S3, again at any point on the surface S3, the electric field will always be away from the positive charge. And your ds vector, this will always be normal to the surface S3. So your ds vector will be this one. Okay, so again here we have E in this direction and ds vector is also in this direction for the surface S3. So you can see that these are both in the same direction. This one, the electric field E is perpendicular to ds. So you have the dot product E dot ds to be equal to E dot ds will give you E ds cos of the angle between them is 0. Then plus, now the dot product here, oh no, sorry. So E, you have E ds cos of, what is the angle for the surface S2? 90 degree. Then plus S3 for S3. E dot ds, this will give you E ds, what is the angle between them? You can see it's in the same direction, so cos of 0 degree. So this one, cos of 0 is equal to 1. So we have drop that one off, and this cos of 90 degree, this is equal to 0. So 0 to anything into anything will give you 0. So all these terms will be equal to 0. Again, cos of 0 will be equal to 1. So that is what we have. Now this E is constant on the surface. Okay, it's same. It is the distance is same from this surface to this surface, and this surface to this surface. The distance is same. So the electric field on this surface and on this surface is same. So this one is constant on S1 and constant on S3. So what you have to do is you take it outside of the integration. So what we have is this one. After taking outside of the integration, we have E integration, surface integration of this ds. And similar here also, we take E outside of the integration, ds. So now if you integrate this ds is a small area here, so if you integrate all the ds, you'll get the whole surface area, which is A. This one also, this is A. So if you integrate this ds, you'll get the whole surface area, this one, which is A. So here instead of this integration, I'll write A, and instead of this integration here, I'll write this A. So now we have 2 EA. So this closed surface integral E dot ds is equal to 2EA. So instead of this one, I'll write this. So we have 2EA, and this is equal to Q by epsilon naught. Now I have to write this Q in terms of the surface charge density. Now the surface charge density, sigma, this is equal to charge per unit area. Okay, and this charge Q is on this area here. So Q is the charge on this area. So the surface charge density will define as charge per unit area. So your Q will be equal to sigma A. So instead of this Q here, I'll write sigma A by epsilon naught. So we have 2 EA here and is equal to sigma A by epsilon naught. Now AA you can cancel. So we're left with this E to be 2E equal to sigma by epsilon naught. Then this 2 will come here. So your electric field E will be equal to sigma by 2 epsilon naught. So that is the electric field at this point, okay, which is at some distance from the plane sheet, infinite plane sheet. And you can see here that the electric field is actually constant. Since sigma is constant, 2 is constant, epsilon naught is constant, so the electric field is also same throughout. It does not depend upon this distance here. Okay, so if it's at this point also, it will be the same. At this point also, it will be the same. If it's at this point, is the same. At this point, is the same. So the electric field does not depend upon the distance of the point from the plane, infinite plane sheet. Okay, it only depends upon this surface charge density sigma. So if we have more surface charge density, the electric field will be more. If we have less surface charge density, the electric field will be less. So that is what we can apply Gauss law for, to find the electric field due to a infinitely charged wire, to find the electric field due to a spherical shell, and to find the electric field due to a infinite plane sheet.